Okay, to continue, as mentioned previously, the fixed support can be introduced at any location along the beam. So, whatever is convenient on your part in drawing the bending moment diagram, so you can place your fixed support at any point on the beam. So if we try to draw the bending moment diagram by parts for the beam, so we place the fixed support at point B. So as shown in our previous uh, illustration a while ago for the simply supported beam. So now you have to take note that the bending moment diagram now contains three parts in our figure. On the second illustration for drawing the bending moment diagram for the simply supported beam. So note that the moment of the forces about B are balanced. So in other words, if we are going to have the summation of moment at point B, which is to the right, is equal to the summation of moment at point B to the left. So it represents the sum of the moments of the forces to the right and to the left of B respectively. So we have here a table showing to us the properties of areas bounded by M, which is equal to K times X raised to N. So we have here for different figures, we could identify the value for our M, which is equal to K times X raised to. So for the application of the moment area method, so to start with, we have your cantilever beam. So if we try to consider this cantilever beam as shown in our figure, so the support at point A is fixed and the tangent drawn to the elastic curve at A is horizontal. So therefore, our tangential deviation at point B with respect to A is the same as the magnitude of the displacement of B. So in other words, our displacement at point B is equal to the tangential deviation at point B with respect to A. So we can have this illustration, and you have here the equation for the tangential deviation of point B with respect to A, which is equal to the area of M all over EI diagram from A to B multiplied to our x bar with respect to relative to B. So that's tangential deviation of B with respect to A now is equivalent to the displacement at point B. For the simply supported beam, the elastic curve of a simply supported beam as shown in this figure is, we have here a calculation for the displacement at point B. So the displacement at point B and the simply supported beam. So we have here our point A and point C. So we're trying to solve for the displacement at point B. So we have here our elastic curve. So we draw a tangent line from point A. So as we draw the tangent line from point A, we could identify our theta A, and we have our tangential deviation at point C with respect to A. And at point B, this is the displacement at point B, and from this elastic curve towards the tangent line, that will be the tangential deviation of point B with respect to A. So for that simply supported beam, to compute for the displacement at point B, so we consider this step. So we have to compute first for the tangential deviation at point C with respect to A, and that is given by this equation. And we have to determine our theta A from the geometric relationship. The theta A is equal to the tangential deviation of point C with respect to A all over L. And we have to compute for the tangential deviation of point B with respect to A using this equation, the area of M all over EI diagram from A to B multiplied 2 bar x relative to B. And we can now compute for the displacement at point B from this equation. The displacement at point B is equal to theta sub A times x minus the tangential deviation of point B with respect to A.